In this lesson on polynomials, we'll review some of the key definitions regarding polynomials, and we'll also review how to add, subtract, and multiply polynomials. First, what is a polynomial? Recall that a polynomial in a single variable x is a term or a sum of terms of the form ax to the n, where a is a real number and n is an integer or a whole number greater than or equal to 0. So n is a positive integer. For each term, ax to the n of the polynomial, we call this number a the coefficient of the term. The degree of a polynomial in one variable is the largest exponent in the polynomial. Typically, we write a polynomial in descending powers of the variable. And when we write our polynomial in descending powers of the variable, the greatest degree term is written first, and we call this the leading term of the polynomial, and the coefficient of that leading term is called the leading coefficient. So let's look at some examples. First, we have 3x to the 17 plus 21x to the 14 minus 3x to the 5th plus 0.2x to the 4 minus x cubed plus 2. Notice here that we have written our polynomial in descending powers of our variable x. So the degree of this polynomial is 17. The highest power of x is x to the 17. So our leading term of this polynomial is 3x to the 17, and our leading coefficient is this coefficient 3. Here we have 9x to the 8, so this is just a single term polynomial. This is a degree 8 polynomial. Our leading term is the only term, 9x to the 8, and the leading coefficient is 9. Next we have negative a third x to the 7th plus 1/2 x to the 6th. This is a degree 7 polynomial. Here we have a degree 2, or a quadratic polynomial. So remember, here our coefficients can be any real numbers. So here our leading coefficient is pi over 2. The coefficient of the x term is the cube root of 13. This is again a degree 2 polynomial. Here we have a degree 1, or a linear polynomial. And finally, the number 5 can also be considered a polynomial. This is a degree 0 polynomial, and the reason for this is that we can think of the number 5 as being 5x to the 0. So a non-zero constant is also a polynomial. Let's look at some examples that aren't polynomials to make sure that we fully understand the definition of polynomial. So first, 3x squared plus 4x minus root x plus 1 is not a polynomial. The 3x squared, the 4x, and the 1 terms are okay, but this root x is not a polynomial term. The reason for this is that root x is x to the 1/2, and remember, in our definition of polynomial, our terms need to be of the form ax to the n, where n is greater than or equal to 0, and n is an integer or a whole number. So for root x, we have x to the 1/2, which is not a whole number, not an integer, so this is not a polynomial. Similarly, 1 over x minus 5x to the 27 plus 16 is not a polynomial. The minus 5x to the 27 and plus 16 terms are okay, but this 1 over x term makes this example not a polynomial. Again, remember that 1 over x is the same thing as x to the minus 1, and to be a polynomial, we need to have terms of the form ax to the n, where n is greater than or equal to 0, and n is an integer. Here we have x to the minus 1, which is obviously not greater than or equal to 0, so this expression is not a polynomial. 2x to the minus 9 plus 4x to the 5th minus 10x cubed plus 1/2 x. The 2x to the minus 9, again the n here is minus 9, which is not a positive integer, so this expression is not a polynomial. 3x to the 4 plus log base 2 of x. 3x to the 4 is a polynomial term, but log base 2 of x is not a polynomial term, so this expression is also not a polynomial. And in our final expression that's not a polynomial, the 5x to the 7, the 3x, and the 1 are all polynomial terms, but our minus cosine x is not a polynomial term. So here are some examples that are not polynomials. Let's now review how to add and subtract polynomials. To add or subtract polynomials, we just combine like terms. So for example, here we have a sum of two different polynomials. The first is a degree 5 polynomial and the second is a degree 10 polynomial. So we combine the like terms across our two polynomials. So for the leading term, we're going to have a 4x to the 10 from our 4x to the 10 in our second polynomial. There are no x to the 10 terms in the first polynomial, so nothing to combine with. Similarly, our next term will be a minus 2x to the 6th. We do not have an x to the 6th term in our first polynomial. Next, we have a 3x to the 5th and a 7x to the 5th. So we're going to combine those like terms to give us a 10x to the 5th. We have a minus x to the 4 and a plus x to the 4. So those will combine to give us 0x to the 4. And then our next term, we have a minus 3x cubed in our second polynomial, no x cubed terms in our first polynomial, so we just get minus 3x cubed. Our next term, we have a 1/2 x squared in our first polynomial, no x squared terms in our second, so we just get plus 1/2 x squared. And finally, our constant terms, we have a minus 7 and a plus 1, which combine to give us a minus 6. So again, to add or subtract polynomials, we simply combine the like terms. In our next example, we have a difference. We're subtracting two polynomials. So again, we'll combine our like terms. Our leading term is minus 2x to the 4th. Next, we have an x cubed minus a 5x cubed. That will give us a minus 4x cubed. Our next terms are the x squareds. We have a minus 5/3 minus 2. So that gives us minus 11/3 x squared. We have a 4x in the first polynomial, no x terms in the second, so we just get plus 4x. And finally, we have a minus 5 minus minus 1, which gives us minus 5 plus 1, or minus 4. So again, to add or subtract polynomials, we combine like terms. To multiply polynomials, we'll use the distributive property and the rules of exponents. So our first example, we have 3x to the 5th minus x to the 4 minus 7 times 4x to the 10 plus 2x to the 5. The first thing we'll do is distribute, so this becomes 3x to the 5th times the polynomial on the right minus x to the 4 times the polynomial on the right minus 7 times the polynomial on the right. So this expression that we have here. The next thing that we'll do is go ahead and use our rules of exponents to multiply through. So 3 times 4 gives us 12. X to the 5th times x to the 10, we add the exponents and get x to the 15. And similarly, we multiply out to get this expression here in our third line. So go ahead and do this multiplication. Make sure that you're getting this expression that we have here. And then finally, we will combine any like terms. So 12x to the 15 will be our leading coefficient. We next have a minus 4x to the 14. Then with our x to the 10 terms, we have a plus 6x to the 10 minus 28x to the 10. That will give us a minus 22x to the 10. And then finally, we have our minus 2x to the 9 plus 9x to the 7 minus 14x to the 5th. So to multiply polynomials, we'll use the distributive property and our rules of exponents, and then we will combine like terms and write our result in descending powers of our variable. One important observation to make when multiplying polynomials is the following. If f and g are polynomials, then the degree of the product f times g will be equal to the degree of f plus the degree of g. And we saw that in our previous example, we multiplied a degree 10 times a degree 5 polynomial, and we ended up with a degree 15 polynomial.